General relativity, step by step. We've been considering the linearized Einstein field equations, searching for gravitational waves. And for the last few screencasts, I've been gradually simplifying or gradually making use of our gauge transformation freedom and our freedom to choose coordinates in other ways that have allowed me to simplify our solutions down to this format here. And we've got the first row of this matrix A dash here being 0, the time component is 0, and the first column is 0. That's what we call a transverse tensor, I guess. Okay, now what I'm going to do is to use the Lorenz gauge. And again, it might look like I'm cheating because I've already used the Lorenz gauge to simplify the linearized field equations. You'll remember that when we imposed the Lorenz gauge, it took the number of terms in the linearized Einstein field equations down from, I think it was 6, down to 1. So that enabled us to solve it nice and easily. But we'll see that the Lorenz gauge has also got other advantages. I'll just write it down again. K mu A, I can't be bothered to write the dash, mu nu equals 0. So there's 4 equations there, one for each of nu, one for each value of nu. And what we'll do is we'll see how it simplifies these terms here. We'll come up with a simplification using the Lorenz gauge. So I'm going to write nu equals t, nu equals x, nu equals y, and nu equals z. So that's k mu. So we're summing over mu, and what do we get? So it's kt a something something plus k, you see I'm expanding nu, x a something something plus ky a something something plus kz a something something equals 0, and the 0 is the Lorenz gauge condition. Let me just fill in those blanks. We're summing over the first index here, so mu is t, x, y and z, and the second index is nu, which in the first line is t, so that's t, t, t and t. We'll interpret this later, but for the moment, well, I'll do the other 3 terms in a minute, but just notice that ATT is this term here 0. The ATT is 0 because it's this one here. XT is that one there, or is it this one here? It doesn't matter because it's symmetric about the leading diagonal. That's 0 and that's 0 as well. So this first line is no help, which is a bit annoying. Okay, well let's do the others. We've got KT, KX. I'll do all the K's in one fell swoop. That's kx plus kx plus ky plus ky plus ky. We'll have a massive amount of simplification here as well, as we'll see, plus kz. Let me just write it all out first. I know we can do simplifications here, but I may as well write it all out first. We'll do all the simplifications in one go. So that's t, 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 x, x, x. Yeah, it should have a dash, but it's more trouble than it's worth. Y, 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 and this one is z, z, z. Now what's the second place? It's t. You see in the second place it's got t, 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 so it's going to be x. Oops, I don't know why it does that. X, 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 x. I'm trying to keep my writing as neat as possible. T, x, y, 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 y. Oh, no, 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 no. The last one is z. Just a minute. Z. The last one is z. That should be an A. That's a z. And here is a z. Beautiful. Now, let me just remind myself what my k vector was. You'll remember I rotated my audience, my coordinates, so that k with the downstairs index was minus omega, 0, 0, omega. And that was the t term, the x, the y, and the z term. So straight away we can see that kx equals 0 and ky equals 0. That's these middle terms here. So what I'm going to do is get my red pen out, if my interface will let me. Is that red? Yeah, that's red. I'm going to zoom in a little bit just to keep my writing as neat as it can be. And what we'll do is we'll cross out various terms. So we've got kx and ky as 0. So kx, oh, that means that the middle terms all disappear. Oh, there should be a k there, but it's gone anyway. There we are. That's nice. Now what else have we got? We've also got that if there's a t in the index, if it's t something or a something t, then that's 0 as well. In fact, I'll just come down a little bit. We can see that this ATT here is this term here, so I'll cross that out. In fact, that means we can cross out all of this. I'm a little bit worried because I seem to have crossed out absolutely... Oh, no, I've got that one as well. I'm a little bit worried because I seem to have crossed out absolutely everything. But we'll see that's not the case. What have I got left? What have I got left? Well, I've got these three terms here. Let me just write that out again. We can expand with this omega here. Let me go back to black. And what I'll do is I'll come down here and I'll write down all the three equations that we've got left. Oh, I should be in black and I'm not. I'm still in red. Let me just go back to black. Black. Still red. I'll have to pause it. Right, sorry, I had to pause it because my interface was misbehaving as well. Where was I? I got 1, 2, 3, 4 equations, each of which has 4 terms, which were an expansion of the Lorenz gauge condition. So we've got 0 on the right-hand side. And lots of these terms here that I've cancelled out in red, or crossed out in red, are 0 by construction, but not all of them. Look, I've got this term here. Actually, I can expand for kz because I know what kz is. Just a minute. Let me delete that. Yes, I know what kz is. So kz equals omega, and I'm assuming, I guess, that that's not equal to 0. So that tells me that omega azx equals 0. It's that term there. We've got omega azy equals 0. That's that term there. And I've got omega azz equals 0, which is this term here. Okay, so what does that do? Let me go back to my little picture. Actually, I'll draw it down here because I don't want to pinch out too much. I'm already having enough difficulty with OneNote as it is. Here's my a dash, written in matrix form, t, x, y, and z, t, x, y, and z. We've already established that these guys here are 0. And now I can fill in some more. I know that zx is 0. That's zx, which is this one here. And it's symmetrical, so that one's 0. zy, which one's that? That's zy. And yz is 0. Is that right? No, it's not that one. It's not that one. It's yz. It's this one that's equal to 0. And we've also got a zz equals 0. Aha! So now we've got 4 terms. And whatever these guys are, it's symmetrical. So this term here, whatever it is equal to that term there. Anyway, look, we're gradually making progress. We've only got 4 terms to think about. All right? Yes, we've only got 4 terms. In fact, we've only got 3 terms because of the symmetry condition. This one, and this one. Oh no, they look like zeros. They're not supposed to be zeros. They're not supposed to be zeros. Just a minute. Let me delete this. Yeah, they're not zeros. Let me just delete those. We've got a term here, call it x. We've got a y. That must be a y, and that's a z. And there's still another simplification I can make. We've just got one more simplification to make. And so we're going to get down to 2 degrees of freedom. Actually, I'll call them x and y and z. I shouldn't really have called them x and y and z. I should have called them something a bit more neutral. I should have called them alpha, beta, and gamma. But I'll do those in the next screencast. I'll stop there. Stop.